and tell us about parameter estimation for graphical models.
Hello, thank you very much for the invitation to speak here. I'm sorry I can't be there in person. I wish I could. Thank you to Raghu and Leo and everybody for inviting me to give this talk. So I'm going to be talking about parameter estimation for undirected graphical models with hard constraints. So I'm going to start with an illustrative example, which is what is called the hardcore model. So, you're given a graph, and I'm going to use the usual notation, the twiddles for neighboring vertices, and use du for the degree of the vertex u in the graph G. An independent set is a subset of the vertex set such that no two vertices in I are neighbors in G. So for example, here, all the colored vertices are an independent set here because there's none of them which have an edge between them. And here, this is not an independent set. Okay, so the study of these independent sets is of great importance in combinatorics, but it also arises in other fields that as I will mention. But one parameter family of probability measures on independent sets, where this lambda, parameterized by this positive real number, lambda, which is often referred to as the activity, is what the hardcore model is. So in the hardcore model on a finite graph, you're essentially giving a probability to each independent set that is proportional to lambda to the power of the size of the independent set. Okay, so any subset has sort of this probability distribution. As long as it's an independent set, it's just simply lambda to the. So the higher lambda is, the more weight you are giving to sets that are larger independent sets. So often, you send lambda to infinity to try to understand what maximal independent sets is, but that's not what my focus is going to be here. So, okay, so, as is well known, you can write this really explicitly in terms of this proportionality, but the hard thing is that you cannot quite compute this z lambda for even moderately sized graphs. Okay, so what do we want? So here's a family of probability measures, which in this particular case, I called it, this is a Markov random field on this graph, which is the same as an undirected graphical model. Okay, and another way to think of this, you can think of it in terms of independent sets, but maybe what will be more useful to us is to think of it really as a configuration of 0, 1 to the v. So you think of each vertex taking a state 0 or 1, with the constraints, and this is where the hard constraints comes in, where the neighboring vertices, the sum of the states of the neighboring vertices must be less than or equal to 1. And so there's, of course, a one-to-one correspondence between independent sets and such configurations by simply assigning to every vertex in the independent set 1 and every one 0 to the complement. Okay, please do interrupt me. I know it's even if it's remote, but I can't see your faces. So please feel free to interrupt me at any time when anything is unclear or needs to go slower or faster. Thank you. Okay, so like as I've said, this hardcore model arises in combinatorics. It also arises in communication networks when you want to assign channels which have to be disjoint different frequencies which cannot overlap in wireless networks. And the name comes from statistical mechanics, where it's a model of hardcore lattice gas, where each occupied site is supposed to be a fat molecule that repels other molecules. And there are many other applications. But what is the question that we want? We want to try to see, can one estimate the parameter lambda of the model by just sampling from this distribution? And so, of course, I think most people would say, yeah, of course, just sample many IID samples from the model, and simply use the law of large numbers and use sort of standard likelihood-based estimates to provide some kind of consistent estimators. And of course, we're interested in the regime where the size of the graph is really large. But really, our question is what you can do with far less information. Getting IID samples from these things is not often available, and it's not something that we want. So we want to really focus on the question that if you fix a known graph, Gn on n vertices, and then you give a single sample from it, from this hardcore measure. When you don't know what the lambda is, you do know what the graph is. Is there a computationally tractable estimator for the parameter lambda of the model? Okay, so that's the question that we want to try to answer. So a standard approach would be simply to take the maximum likelihood estimate. However, this is computationally intractable due to the normalization constant C lambda G that I mentioned. So instead, one could try to take what is called the maximum pseudo-likelihood estimator, which was introduced by Besag way back in 1974-75. And the idea of that is if you're given a certain sample, so you're just given 1 omega samples on each of the vertices, which I'm just always going to label from 1 to n for simplicity. And you, I'm sorry, this is missing. This should be the argmax over all lambda of this. What is this? This is called the log pseudo-likelihood function. And what is it? It's of product form. And of course, we know that even though the normalization constant is hard, so we cannot compute probabilities, we can compute conditional probabilities in a tractable fashion. So the idea, this f lambda I for each vertex is the conditional probability of the state at vertex I, given the states of all the other vertices. Okay, so you have these this conditional probabilities, which you sort of take a product over all I, and the idea is, okay, this is a pseudo likelihood estimator. There's no a priori reason why you think that this, looking at the argmax of this rather than the maximum likelihood should work. But, Besag did show that this can work well in certain situations. So one thing that we wanted to look at is to try to see how well this works in this context. So I should mention that, and I have given references at the end, that people have looked at these kinds of the maximum pseudo likelihood estimator based on one sample for easing models. So these are these soft models, ferromagnetic models. And so, but the structure of models with hard constraints is very different. So let me explain. So let me first tell you what is a result that we have in the case of the hardcore model. So like I said, you've given some graph on n vertices, you take a single sample. And then if you define your Cn is just to be, it's counting. So it's just the number of vertices which have one. So it would be the size of your independent set, if you want to think of it that way. And then Un sigma is another count of vertices which are 0 and have all its neighbors 0. Okay, you can, and what is so special about these vertices? Well, the thing is that if you count each of these vertices are those that if you change the value from either 0 to 1, then they would still be an allowable configuration. So that's why I call them the number of free vertices or sort of unconstrained vertices, and that's why I have U, and C is sort of the count. So U is sort of free, unconstrained vertices where you could change the value and you would still get a legitimate configuration in the sample sigma. Okay, and it turns out that in the hardcore model, if you work out these conditional distributions and look at the argmax, the maximum pseudo likelihood estimator, in fact, takes a very nice form in this particular case, which is just the ratio of the number of ones divided by the number of free vertices. Okay, and it's rare to have such an explicit form, so that's really nice in this particular case. And it is at least intuitive because of, that you would, that this should be larger if the number of ones are higher. Your estimate for lambda hat, for the lambda would be higher if the number of ones were higher. And, that at least makes sense, that it's proportional to Cn in some way. Okay. So then the theorem is that, so this is the estimator that you have in the hardcore model, and that if you consider a sequence of graphs that has uniformly bounded average degree, so that you look, you just average the degree of each vertex in the graph, and if that is finite, over the uniformly finite, then this estimator lambda hat does actually converge to the true value. but also at a rate. So at a rate of sort of square root of n, so m over square root of n. So it gets square root of n to the minus half close to the true value as the n gets large. Okay, and this is for any sample. You're just taking one sample and you're trying to get the value of the lambda. Okay, any questions? Okay, so if you look at, I mean, there are, of course, all bounded degree graphs will satisfy this condition, but also realizations of random graphs like sparse Erdős-Renyi graphs and things like that would also satisfy this condition of a bounded average degree. Okay, so this is just sort of a start of just looking at one particular example. But let me tell you a little bit about the idea of the proof. So you look at this sort of log pseudo-likelihood function, which I'll call NLP to be short. Remember that these were the conditional probability mass functions of sigma I given the rest. And you obtain this lambda was the argmax, right? So you have to, so essentially you just have to compute the derivative of this, show, and then this is random now because you have this sample. But you want to show that it is very concentrated around 0 as the true model parameter. So for those who are sort of used to some of these kinds of inference questions for Markov random fields, you might worry that, is this really possible even in the case when the associated Markov random field on the infinite graph doesn't have a unique Gibbs measure, or in other words, when there are very strong correlations and you don't have correlation decay in your system on the graphs between configurations at different vertices, you have very strong correlations, then sometimes you think that inference might be hard. But in fact here, because we don't use correlation decay, which is often used in this case to try to get concentration, but we use another method of what's called exchangeable pairs to show concentration, we're able to sort of get this consistent throughout for all activity values. Okay, so once you get the derivative, you show it's concentrated, but then you also need to show that it's somehow asymptotically strongly concave. And for that, you need to understand and establish certain properties. So of course, concavity is needed to actually show it's a maximum, right, at that point. But by establishing and some sort of uniqueness is needed. So for the strong concavity, and you do this by establishing certain properties of the limiting normalized log partition function. So the partition function being that normalization constancy. And so that requires trying to understand the behavior of the hardcore model for large N, understanding the partition function. Okay, so that was just sort of a beginning to try and see whether these kind of pseudo maximum likelihood estimators are likely to be useful for hard constraint models. And so then we wanted to try to understand more generally whether you can do this kind of parameter estimation for more general classes of hard constraint models. So what do I mean by you can sort of formalize what is a hard constraint model in the following way? You take the set of states that you have. So in the hardcore model, it's just 0 and 1. And you construct a graph on the states. If you allow a 0 to be next to itself, then you have a loop. So you put an edge between 0 and 0. You allow 0 to be next to 1 it's not in your sort of configuration space. So neighboring vertices can take values 0 and 1, then you put an edge, but you don't allow a 1 to be next to 1, so there's no edge between 1 and 1. Okay, so this is what is a constraint graph whose vertex set will be the number of states that each vertex can take, and the edges determine whether the constraints, essentially. So the more edges you have, the fewer constraints you have in your configuration space. Okay, so in the particular case of the hardcore model, right, this was the constraint, like I said, and then you can identify this space of configurations with homomorphisms from the graph G to the graph H, because then it disallows two neighboring vertices to be 1, 1 because there's no edge over here. Okay, so that's another way of thinking about so by hard constraint models, we mean models where each particle takes values in some finite state space, And the constraints are induced by this kind of a constraint graph, which forbids certain neighboring configurations. Okay. So then we wanted to try to understand what is the role of this sort of, so let me give you some other examples. There's something called the Widom-Rowlandson model, which is comes up in, again, statistical mechanics. It's a model of a binary gas where there are two kinds of gas particles which repel each other. So here it's 1 and 2, and 0 is just the empty site. And so 0, of course, connects with everything, but 2 cannot be next to a 1. So there's no edge between 2 and 1. So that has this H graph. And then there's, of course, very well-known coloring models where you can, if you have K colors, then here in this case, you have 5 colors, and you can have any, it's really like the complete graph is the constraint graph. None of them have loops. So you're not allowed to have 2 neighboring vertices of the same color. That's the only restriction. And that can be looked as the configuration space, simply homomorphisms from this complete graph to, from the graph G to this complete graph. Okay, so we want to understand, this is now just the configuration space, but we're interested in some probability measure on a family of probability measures. So again, given some simple graph G, and then you're given a constraint graph, which is not necessarily simple. It could have loops, as I said. Then an H coloring of G, as I said, is just an assignment of the colors to G in the sense that I said that you can't have neighboring vertices which don't have an edge in H. And then the probability measure, so the model that we're interested in, probabilistic model, is just a probability distribution. And now you have parameters, Q minus 1 parameters. In the hardcore model, you had 1 parameter because you had 2 states. Here you have Q states, and so you have Q minus 1 parameters. And again, the probability distribution here, of any configuration is proportional to the product of lambda to the, whatever the sigma, the size of the number of configurations of that size. Okay. So given a constraint graph and another graph Gn, so we want to, again, ask the same question. Given a single sample from the H coloring probability distribution, is there a computationally tractable estimator for the parameter lambda of the model? And in this case, now the lambda is a multi-parameter, so it's a vector. And it turns out that in this case, there's another quantity of interest. So we had the C and UR, but here the U is a little more complicated. So you can still think of these U as these unconstrained vertices, which I want to think of them as that if you swap them, then they're still allowable configurations. And one way to just write that is just to say that, so here I'm looking at with respect to a particular state. Okay, so if I look at the state R and I want to see whether this vertex is free to change to state R, then I need to ensure that all the neighboring vertices are sort of in the neighborhood of R, right? So are taking states that are in the neighborhood of R in my constraint model. That way, if I change this particular vertex V to R, then I'm not violating any constraints in the constraint graph. So you have this quantity, which is the set of states of sort of, I call it free particles with respect to the state R in the neighborhood of V. And then you note that this so as I said, I'll refer to these as R unconstrained vertices in the sample. And just make a little note that obviously, since this is an allowable configuration itself, so it is this count of these number of R free vertices is obviously greater than or equal to the ones that are already taking the values R. So that's just something I just wanted to observe. So this is just the count of the number of vertices which have state R in my sample. Okay, so if I fix a constraint graph, this is a minor, almost any constraint graph, this is a minor restriction that I won't go into. And then a sequence of graphs that satisfies, again, another minor restriction that you actually have a feasible configuration. that your H doesn't make it impossible to have any configuration at all. So you just don't want it to be the empty set. And it has, again, uniformly bounded average degree. Then once again, you have a root n consistent. And now here you have the Euclidean norm here in terms of measuring the distance between the parameters. Okay, so then your maximum pseudo likelihood estimate is again square root of n consistent. Okay, any questions? Okay. Okay, so and so let me tell you a little bit on the assumptions, because now here I didn't I should have spent some time on this. So here there's it's not, remember for the hardcore model, we simply had only this condition on the degree of the vertex. But here there's an additional condition that when I choose the sample, that sample should have a certain property, which is given by here, which is, you know, something that you want to sort of deconstruct and understand. What is this assumption saying, that if I take a large enough sample that has this property, when will it have this property? Okay, so remember what this is saying, that the sort of fraction, because there's an n here. So if I divide this would be the fraction of our unconstrained vertices, you know, should be of a positive order. You know, they cannot vanish to 0. Okay, so that means they are of order n for every r. Okay, so you can't have sort of just some states having very, very low representation in that sample. And so the consistency result for the H-coloring model, like I said, I'm going to call this additional condition a rainbow positivity condition for following reason. So you remember that this was greater than the count. And so in a sense, if you could show that the expected value of any configuration under your in your model in a neighborhood of the true parameter, that the expected number of vertices with state R will be fraction, not number, but fraction of vertices. Your C bar is a fraction. Then if that is strictly positive, as n goes to infinity, then you can show that this condition is satisfied. And we call this a sort of rainbow positivity condition, because that means like all the states, so all the colors are represented, you know, with at least some order n positive fraction. So, but you know, that still is something about the sample, and you might just want to say, I want to understand it in terms of just the model, and I don't want to be looking at the sample. So it turns out you can put a condition on the constraint graph itself, and you can say that if there is at least one unconstrained state in the graph, that is, there's one vertex that's connected to all other graphs, all other vertices in the constraint graph, then this rainbow positivity condition is automatically satisfied. Okay, so you can check that. And so that we had to show using sort of studying these Markov random field models. And this is true, for example, for the multi-state. Of course, we know that the 0 you can always is something that can connect to everything. So it's true for a hardcore, also an extension of it called the multi-state hardcore, Widom-Rowlandson models, etc. So this is nice because it's just a sufficient condition simply on the constraint graph. And you know, you don't have to look at the particular sample and see what's happening. Okay, so again, the idea behind the proof is, you know, to look at this log pseudo likelihood and now show that the gradient is concentrated around 0. But the proof now of showing that it's strongly concave in this more general setting is much more complicated, and it involves relating sort of the Hessian matrix to some other covariance matrix of a certain distribution and using facts about its eigenvalues to show that it's negative definite whenever the rainbow positivity condition holds. So that's where the rainbow positivity condition comes in showing strong concavity of this at the true value. And in fact, one can show that this log pseudo likelihood, I mean, the gradient is even 1 Lipschitz. And that's very useful because I didn't really tell you what the estimator here was, right? In this particular case, for the hardcore model, I wrote it down explicitly, but in the case of more general constraint models, the estimator is given sort of implicitly as the unique zero, or with high probability unique zero of a certain, quite explicit function. I'm going to flash the form of the function, but it's really not important. I just want to say that it can be written down very easily once you have the sample. So it's just a simple expression here where you just have to look at the neighbors of each vertices in that sample and then just compute something simply. Okay, so you just have to sum over the vertex. Okay, but because of this, and you might say, okay, it's a zero of some function, but because of the one Lipschitzness, in fact, you can do a simple gradient descent algorithm to find this zero. So because you're talking about an algorithm that can actually estimate, this is not just an existence result. You can have a simple algorithm to actually compute this. Well, I mean, to get close enough. Okay, so I thought I should talk a little more about all the conditions. So as I said, that is sufficient condition for in the general H coloring models is that you have this rainbow positivity condition, and that a sufficient condition was this nice condition on the constraint graph. But there's clearly one model that I mentioned that doesn't satisfy this, right? For instance, the Q coloring model will not satisfy because every vertex is constrained to not have itself as a neighbor. So you might think, okay, then this theory that you applied doesn't apply to a very important where you want to estimate the parameters of the regular coloring model or the K coloring model. But in fact, even though the sufficient condition for the rainbow positivity fails, and the rainbow positivity itself could fail, what we show is that you can show that the MPL estimator for this model is still root n consistent on any graph GN that has uniformly bounded two neighborhood rather than just one neighborhood. Okay, so there is a little bit of a trade-off here. So because of the lack of time, I won't have time to sort of explain where the two neighborhood comes in, but I do want to talk a little bit more about the trade-off between, the rainbow positivity condition and putting extra conditions on the graph, right? So here I'm putting extra, like I'm looking and I'm saying, well, I don't have this nice condition on the sample or on the actual H, the constraint graph, but then if I put extra conditions on my sequence of graphs, then I do, in fact, I'm still able to get consistent estimation. So a natural question in this context or is that you might say, okay, so maybe any H coloring model, maybe it will be consistent for, a small enough sequence of graphs. You could ask that question that if the rainbow positivity doesn't hold, can you just transfer it onto a sort of stronger condition on the GN? So for instance, is the uniform bounded two neighborhood enough for all models without the rainbow positivity? And the answer to that is no. And you can construct a graph like this. So if you have an H coloring model, this is the regular, so if you have, you have over here two vertices here, there's actually a complete graph here. And on Q minus one vertices, if there are Q states altogether, so there's a complete graph on Q minus one. And this sort of, and it's a bipartite structure. So this gives a counterexample where you can actually prove that you do not have consistent estimation at all. So it's not just that you can prove that you do not have root n, but root n consistent, but you cannot have any consistent estimator. And of course, you might think that these non-existence results are a little harder to prove, but the way you do it is by showing that if you had a consistent estimator, you would need certain hypothesis testing, test one, test two errors to behave in a certain way, and you can prove that they cannot behave by studying the difference between two models with different parameters. Okay, so it's not possible to have consistent estimation for all H coloring models, but we did show for the Q coloring you can by just putting a little additional condition on the GN. The other question you can ask is, in the Q coloring model, can we relax the uniform average two neighborhood boundedness back to just the one neighborhood? Was it just why can you get away with that because it was okay for the hardcore model? And why do we really need the two neighborhood boundedness? So we could also show that there exists a sequence of graphs with bounded maximum degree, so it's bounded degree, for which consistent estimation is impossible. So this is quite a simple graph. So of course, it's not maybe one that you would encounter, but it's just a counterexample. So here you would have sort of a union of n disjoint triangles and then a fixed graph, a line graph of fixed size, which is not increasing with n. And then you can easily see that the vertex 3 cannot belong to any of these, can never be in any of these because it can only be the neighbor of one vertex. So the state 3 can never be found on these triangles. And so they can only be found here. So the fraction of these 3 states is really going to go to 0. I mean, as n goes to infinity. And that's not enough. Of course, it just says that the rainbow positivity condition fails, but then you can show that in fact, consistent estimation is not possible. And obviously this is a graph which has very nice bounded maximum degree of just 3. Okay. So just to conclude that, we can develop sort of computationally feasible algorithms to estimate parameters of graphical models with hard constraints for a large class of, sort of sparse graphs or bounded maximum degree graphs, and obtain, in fact, just even a rate of convergence of the estimator as the size n of the graph goes to infinity. And there may be other models besides the hardcore model for which, the estimator has a closed form solution. We don't know, but we can anyway compute it using gradient descent for the class we know. However, we don't know, further conditions when the rainbow positivity condition fails. Is there a more general condition other than we just studied Q coloring models? So that's one question. And maybe another more relevant thing for sort of when you want to actually look at finite size and a particular problem of n, we do get only asymptotic results, and it would be nice to try and sort of bootstrap our results more to sort of get finite n accuracy estimates so that you know how large the graph has to be before you can get a reasonably close to the estimate, to the true value, that the estimate is good enough and the error is small enough. These are just some relevant references of Besag, was the person who introduced sort of the pseudo-likelihood method. Saurav Chatterjee used it in the context of estimation in spin glasses. And then there were sort of several works that tried to do things in the context of easing models. And recently this has also been used more in other contexts, the pseudo-likelihood in using easing type models, but coming from other learning problems. This is the work that I was talking mostly about. I think my time is up, so I will end here. Thank you.
Any questions?
Could you say a bit more why we cannot get finite and guarantees? I mean, it looked like you have no components, exchangeable pairs to show the gradient is small, etc. Like what?
Yes, I mean, I think that it could be possible, but what we were trying to do, so, this is somewhat recent work. It's not like we tried finite n very hard, but it's not completely straightforward because there are, we use exchangeable pairs to get concentration, but there's a lot more because you also have to understand this concavity, and the concavity is also with high probability as n goes to infinity. And that's the part which hasn't been finite n-ized, but it's certainly something that's doable, I believe, but we haven't spent enough time on it. That's why I put it as a question that I think is doable and should be done, but we haven't yet done it. But it's not completely trivial. It requires a little bit more of estimation. Like I said, that in the case of the general H constraint models, you have to understand better the eigenvalue of this certain covariance matrix, and you need, adequate bounds on that. But I do think it is feasible.
Thank you.
If not, let's thank us.